Dr. MJR Educational and Research Institute. It's give me immense pleasure to welcome you all today for the day 5, the 6 days virtual faculty development program on transformative approach in computing paradigms, machine intelligence, and quantum computing. Organized jointly by the Department of Computer Science and Engineering in association with Center of Excellency, CMT, and Department of Cybersecurity of Dr. MJR Educational and Research Institute. I also extend my warm welcome to our Dean and HOD, Dr. S. Geeta Ma'am, Department of CSE, and Dr. Dinesh Kumar Sir, Department of Cybersecurity. Faculty participants, research scholar who have joined today's sessions. So today we are privileged to have with us Dr. Sheik Shabana Anjum, Senior Lecturer, Taylor University, Malaysia. To introduce ma'am, now I invite Dr. Anthony Sir, Professor, Department of CSE, to give the brief introduction about today's speaker.
Good afternoon, everyone. It's my pleasure to give the introduction about today's guest. Dr. Sheik Shabana Anjum is a senior lecturer in computer science at Taylor University, Malaysia, with over 7 years of academic and research experience spanning the Internet of Things, artificial intelligence, data science, Industry 4.0. She holds a PhD in computer science from the University of Malaya and has built a progressive career across research and education, including the postdoctoral fellowship at the University of Malaya and a leadership role as head of praxis industry and community engagement at UCSI University. At Taylor's University, she has received a program coordinator for the Bachelor of Computer Science graduates, an IEEE member with an international research profile. Dr. Anjum is driven by mission to advance sustainable technologies and bridge academic innovations with real world impact. Her research contributions span wireless sensor networks, energy harvesting, conjunctive radio, and machine learning applications with publications in Scopus Index journals and international conferences. She has received multiple awards at international competitions, underscoring the calibre and relevance of her work. Beyond research, Dr. Anjum is deeply invested in curriculum development and postgraduate mentorship, forecasting the next generation of technology leaders equipped to navigate the evolving demand of a digitalized world. Welcome, ma'am.
Thank you, Dr. Anthony. Thank you,
Shabana?
Dr. Geeta.
Yes,
ma'am.
happy to see you after a long time.
Yeah, likewise, same here. Thank you, Dr. Geeta. Thank you for the opportunity. Thank you so much.
With pleasure, always to have you as our session speaker.
Thank you, ma'am. Happy to share my knowledge. Okay. All right. So we shall start now. Can I start, ma'am?
Yes, you can start.
Yeah, okay, thank you. Hello, participants. Very good afternoon. So the brief introduction was already given about me. So I am here today to share my talk about intelligent healthcare. So I'll just share my screen. Give me a moment. Okay. Can you see my screen?
Yes, ma'am.
Okay. All right.
Yeah.
Okay. So today my topic of discussion is about intelligent healthcare. And since we are having the concept of talking about through this faculty development program, we have the concept of talking about machine intelligence combined with quantum computing. So my talk today would be, how machine intelligence will actually help us to dive and make use of different technologies which we all are familiar with, like your Internet of Things and even big data analytics. So how the intelligence through machines will help us to deep dive or improvise the futuristic medical innovations. I will be discussing the existing medical innovations that we already have from many different applications or platforms, or even the innovators who have given us different solutions so far, and also about some futuristic ideas which we as people who are in technology, who are like we drive a workforce where we teach students about how we can take forward the technology, take forward the intelligence from machines, from different technologies, and apply it, be it in medical field, or be it in smart farming, smart city, sustainable innovations, for anything, right? So we as educators should be able to see how we can harness all of these technologies, which is your machine learning, your AI, IoT, and also your big data analytics. Is specifically today's talk, we will be dealing with medical related innovations. Okay, so let us start. Okay, so why this conversation matters? Why do we need to think about this in the first place? Because as we know, clinicians or even doctors, the people who are working in medical field, they don't have time, or to if you might see, they don't have the prior kind of intelligence with which they can predict a person getting a heart attack, for example. Okay, and or a person, or any kind of data that is there in hand. How can we bring about useful insights, or how can we bring about the patterns with which as human beings they cannot see through the data that they have in front of them? So how can technology help here in how can machine intelligence specifically help in medical field? So machine intelligence, basically, it makes us to read patterns, okay, which of course the doctors don't have knowledge, or don't have the intelligence to read those patterns. Might be they will look into the condition of the patient, and might be they'll just give a prescription and they'll say, yes, okay, this is a remedy, and with this you can get all right. But what is the hidden pattern behind the data, or hidden pattern behind what has happened to the patient? Yeah, so when machine intelligence is in place, we can take forward, or we can convert whatever the experience of a doctor plus the intelligence from a machine. So we can combine both of this together, and might be instead of giving prescription, we can have remedies which can prevent that possibility to happen, or with which we can prevent the patient getting into such a situation. Okay, so connected devices Connected devices as in what? Any kind of devices which the patient is wearing. So I'm pretty sure all nearly 239 240 of you here might be wearing any, like any watch which is a smart watch, which is currently, at least few of you, few of you would be wearing a smart watch which is currently measuring or detecting your heartbeat, or looking into how many steps you're taking every day, how much you're walking, and how well you have slept. So what is all of this? When a device is connected to our body, we actually get continuous stream of data or continuous stream of signals. So with this, what can we do? We can bring about, or we can give scope for the machine to be intelligent enough to convert all of these continuous stream of signals or data into something useful, into some decisions with which I think at least to some extent we can turn all of these analytics, or turn all of these continuous stream of signals into something useful, into some insights or decisions with which might be we can bring about a lot of changes. Yeah. So decisions at the bedside of the patient. So not necessary that the patient has to go into some problem, some issue, some health issue, and only then we should give the solution. So right before itself, all of these continuous stream of signals can make us prevent untoward situations. So machine intelligence, the model learns from the data. So basically, if I want to put it in clear terms, what do you mean by your machine intelligence? Any data that is there. So the models, the AI, the machine learning models try to learn from the data. They train themselves. They try to give some kind of insights to you with which you can take proper decisions, and then again you train back based on different set of patient data. So it's kind of a loop which goes on forever, rather than considering it as a single line. Yeah. So Internet of Things, we know, we already are familiar with this technology, but in with regards to medical applications, the sensors, the IoT sensors should never go to sleep or should not rest. So there is continuous, that is why we say that there's continuous stream of signals. There is continuous sensing. And why do we have big data analytics here? Because the people who get into health issues, or the population is huge. We cannot just create models that can take in data only for few set of people. So it has to, in case of epidemic, or in case of pandemic, it's very important that all of these models should work. It's not that all of a sudden when the data is too huge, it should run into an error. So we should be able to handle humongous amount of humongous data as well. So again, when we look into all of this, so what will be the takeaway of today's discussion? So we will be looking into the overall landscape of how your machine intelligence, your IoT, and your big data analytics, everything merged together and can be used in your medical field, or for your future healthcare. And then I'll also be showing you YouTube videos, the real world implementations that so far like the companies or the platforms have already come up with, the real-time case studies. We will also be looking into it, which have deliberately changed the patient outcomes. And also we will be looking into the trade-offs. Of course, nothing comes as such, so everything has plus and minus. So we will be looking into what are the ethics that we have to follow, especially since it has patient data involved, and what are the privacy and the trust concerns, and of course, as technologists, as academicians, how can we take forward this knowledge that we will be getting today out of this session. So how the session is actually structured is I have divided it into 6 sections. So first we will be looking into the foundations, then we'll be looking into individual topics like what do you mean by your machine intelligence, what does Internet of Things mean, and how can this be related to medical field or healthcare applications, big data analytics. Okay, and then fifth one would be how all of these three merge together and what is their convergence point, where is the point where they converge together, and what do we owe all of these patients in terms of ethical concerns. And then we will be looking into the future roadmap ahead. What is the future ahead? What are the cautions that we have to follow as technologists or even as healthcare providers, and what is our role? Okay. All right. So starting off, the first thing is the foundation. So if you all are not aware about the terms, we will be looking into what are these terms, basically the foundations, and how can it be correlated to your intelligent healthcare. Okay, so not we should make sure here that just the tools is not important. How your ideas connect with each other. Now presume that I tell you you want to invent something for the society, or you want to do something for the society, and you as a technologist want to build up an app or a solution or a system with which I can make the healthcare more intelligent. Might be we have our personal connections over there. Might be we would have come across people from our own family facing health issues, and we want to solve it through our solution, through our technology. So what would you do? How would you make use of? The question here is how, what can we do to make use of the technology to improvise the healthcare which is there currently, what we can do. Okay, so at the end of the session, might be my attempt is for all of you to give a thought about it. Okay, and might be go through the papers and go through all the things that I'll be sharing with you today and come up with any idea. Yeah, so let us start with the foundations. So 3 technologies and 1 continuous loop that doesn't stop. And why do I say that it's not a straight line and it's a loop is because we are not here to just say that the device is sensing something. The device that I'm wearing is sensing something. It's trying to tell, it's trying to understand something, and then I just get a remedy. No, I don't want it to be a straight pipeline. Like I want it to be, you know, a, a loop which first senses what is the problem from my body. Okay, so any device which captures the signal from either my body, okay, and from the clinic, or if I go to the clinic for any checkup, my IoT device is trying to sense the information or sense the readings and have the information stored. Now the next part is AI. Okay, when I embed AI into my IoT, my AI model, what does it do? It gets the signals from my IoT device and then it interprets. It interprets into what? It interprets these signals into prediction, into something, some useful information. Okay, some useful derivation. Like, what am I trying to derive out of the signals that my IoT device is sending or sensing? So after I interpret and after I get those predictions, what does my data analytics do? It decides. It decides and it converts all of that into evidence. Now, what this evidence will actually do, it will be converted to an appropriate action. Okay, and that action is sent as a feedback to the patient again. So it comes back again to the patient who is basically wearing the IoT device, or who is basically having the IoT sensor. So that is again got here. And again, what happens is, again, the sensing happens, the AI understands, and again, the data is being decided. So these technologies, if I want to make use of them in a medical, in intelligent healthcare, they cannot be used separately. Okay, they cannot work alone. So what do I do is I combine all of them together, and I am having a single loop. So together they form the loop of sensing the information, sensing the data, understanding what is that data, and then giving me action, or acting, giving me the response that I'm supposed to take, and sending it back to the patient. So feedback is returned to the patient and the system from where it started all the way. So that is the reason why all of these three technologies combine together and they form a continuous loop. Okay, so what are the key terms that we should be aware of? Machine learning, yes, of course. Um, you have the data with you. Okay, you have the software. So in which machine learning is embedded. So what the software will do is it keeps improving as and when the data comes in. So every time you have a task, every time you have a task for my machine learning model to perform, it learns from the data. It learns from the data, rather than having, like, fixed analogy, fixed rules that I should behave like this only, I should do like this only. So if A input is given, I should give only B input. No, it doesn't work in that way. So whatever input is given, whatever data is fed, based on that, my model learns. My model improvises each and every time the data is got inside. Okay, so this is machine learning. Deep learning, we have, like, layers of network that that learn through patterns from images, text, or signals. Okay, and then you have the edge devices. The next one is the edge devices. So rather than having a centralized system, or sending over the important data to some other place, what do? I have edge devices. So wherever the data or information is collected, there itself the data is processed. So this is edge computing, edge devices. So wherever whichever devices have this edge computing in it, so they are termed as the edge devices. And then you have the big data. So why do we need to have big data in place? Because, as I said, we need to have the capability of data sets being very huge. So whenever I have humongous data involved, the models should be capable enough to handle the data sets that are too large. So this also makes us think that, data sets being too large, how fast is the processing done? Or, how can different tools be handled when all of the data sets are, being too large? So why we have the quantum computing here is, again, instead of traditional computers being chosen to solve the the problems or issues, we have quantum computing. So quantum computing is basically using your qubits. So we have already had the session before where we learned what do you mean by your quantum computing. So we use the qubits, the quantum bits, to explore the many possible states instead of the traditional zeros and ones, which the common computing does. So instead of that, if we want to solve two complex problems, it's important that we make use of the technology where we have quantum computing in place. And then you have the federated learning. So I hope you all must have come across this phrase, where it says, where it has the concept though we say that the rest of the technologies help the medical field to be improvised, training a shared model, without moving the patient data. So if we want the patient to be treated at many different hospitals, but we don't want to move the patient data, and we want to have it in just one place, then federated learning can come come as a rescue, where a shared model can be trained without actually moving the patient data. So training one shared model across many hospitals without even the need to move the patient data. So each hospital keeps its own data. So only the learned patterns, or the patterns deducted from the learning, that only travels. So this is a concept of federated learning. So why we choose all of these technologies is because I would want all of you to think which of these 6 terms is can be mostly used in the field of medical applications, or which is more underrated. Like, how can we combine, or you can use it solo. So a point to be noted, or a question to be asked here or raised is, how can each of these technologies be leveraged or be used for improvising our medical or intelligent healthcare. All right. Next, this is just an illustration for discussion and not a deliberate, a forecast. So what this slide basically tells is that you have three rising curves, as you can see here. So one is machine intelligence, as the color code says, and the other one is the IoT in healthcare and big data analytics. So you can actually see, you can see from the graph that big data, big data is this one. So big data started highest in 2018. Okay, so it started highest in 2018, and IoT is in the middle. Okay, so IoT is over here, so it's in the middle of machine intelligence and your big data analytics, so right during 2018. And AI, if you can see, AI, the machine intelligence, has been the lowest during 2018. And as the years progressed, by 2022, you can see, by 2022 is the point where you can see AI has overtaken. AI has basically overtaken, big data. And by 2026, if you can see, all the three are converging together, and they are converging at the top. So what is the point to be noted here is, we cannot say that it is just one technology with which the medical, the intelligent healthcare can work. So as years go by, as our needs are increasing, as our healthcare is being prioritized, we can say that the convergence is happening in real time. the convergence, yes, it is happening in real time. And we do need such deployment to be done across different layers, across three major layers, where one can show the intelligence from the machines, one can actually sense the data from the patient itself, and one can give us useful analytics. Okay, so this field is moving very fast, as you can see through the illustrative trajectory given here. Okay, next, since we have seen, or we have got the glimpse of the foundations, we will, next deeply dive into our second section, which is, machines that learn to reason about health. So from pattern recognition today to quantum assisted discovery tomorrow. Okay, so why this is important? Because machine intelligence is where the hype is the loudest, okay, and misunderstandings are the deepest. Correct. So if you can agree with me, you can like understand what I'm trying to say. So machine intelligence is having too much of hype these days, but at the same time, when we get into any problem or any issue, misunderstandings tend to be more deeper. So in this section, we will be looking into how machine intelligence will help us, and how they take us from pattern recognition to quantum assisted discovery in the future. Okay, all right. So we have in machine intelligence four things that models actually perform. Okay, four functional categories that you can see in front of you. So first one is seeing, that is monitoring or looking into. The next one is predicting. Then the next is reading and writing, and the next one is optimization. Okay, so almost every clinical AI product in the market today, okay, falls into one of these four aspects. Okay, so what do you mean by your C? Okay, what do you mean by your C? So this is your imaging AI, like um, what images are there. So your AI basically goes through the images, and then it gives the strongest evidence base. So the applications that you can use here is detecting diseases from scans, from retinal images, so on and so forth. Okay, the next one is predict. Predict means what here? It is the risk stratification. So how much is the risk? Okay, so it's the most consequential. So it shapes who gets the more attention, like flagging the deterioration, or flagging or warning us about the risk before it turns into a calamity, or before it turns into a crisis. So that is your prediction. Okay, the next one is reading and writing. So this is generative AI, okay, for documentation purpose. So this is actually summarizing or giving the evidence or drafting letters. So this is actually changing very fast right now, so it's improvising. And then you have your optimization. So optimization here is operational AI. Okay, so operational AI means what? It's mostly invisible to patients, but we can say that this is the most necessary and largest economic driver. Why? Because it schedules, it triages, and then it routes the resources very efficiently. Like, if there is any pandemic, how many vaccines are available, how many patients are coming to a particular hospital, how many patients have got the first dose, or how many patients are are put up into home quarantine. So according to that, how do I efficiently optimize the resources? How do I schedule it? How do I have the route optimization? So all of this comes under optimize. Okay, so why are we having these four things here that the models perform in your medical field with regards to machine intelligence is you have to be very sure about how we can use the clinical products or clinical AI solutions, and how we can put across it in different aspects that we have here, which the models are trained to do. Okay, so the context is more important here. And it's very like it's very attention seeking thing that we should be able to train our models into. Okay, and how do the clinical models learn? So the next question is, how do a clinical model learn? So it is a 5-step horizontal pipeline that you can see here. So it is first to collect, then next to train, then to validate, then to deploy, and then to monitor. So when I have a clinical model, so what do I do? What do I actually first do is the model is trained first. Okay, when after the data is being collected, like scans or outcomes or patient records. After the data is collected, it is trained. So the model adjusts itself, and it makes sure that the mistakes are not done, and then the validation is done. So mostly this part is skipped. So this is more important. Validation has to be there, especially because it involves clinical data. Okay, it involves clinical data. Validation has to be there. So on unseen patients also, the model has to be tested, and then put it besides the clinicians or the doctors. But you have to make sure that this model cannot replace them. It is only as a tool to help the clinicians, not replace the clinicians. And then monitor the results. Okay, retrain them if necessary. Okay, as the practice changes or as the patient change or the population change, and then the loop continues. So again, it comes over here, and then the loop never closes. So this is more important. Many clinicians, right, believe that AI is a magic, and it just like that happens, and they don't give importance, especially to this step, as I mentioned. So this is more important. They miss the validation, the step where you test the model on the patients, that the patients that the model has never seen before. Okay, to confirm that it generalizes, it performs the generalization. So without proper validation, any model, okay, that performs perfectly in training. Okay, so it performs perfectly in training, it's deployed successfully, and then the results get monitored. So without validation, if all of the other steps are also successful, then I would say that it can fail catastrophically during either the deployment step, or even like if it fails here itself, it cannot go to step number 5. So that is evident. So this point here, why I am pointing out, is because this is a responsible. Okay, clinical models would actually be responsible for if such a catastrophic thing happens, it would be responsible for a large fraction of real world AI failures, which we are not ready for. So we have to make sure that um, whatever clinical models we are building, or we are using, should be able to perform successful validation. Okay, because populations change, patient populations change, and practice guidelines also get updated, especially in medical field. So it's pretty obvious, right? If a model is trained okay, if I perform this step in 2022, okay, so I'm training it in 2022, but I'm not rechecking it again, okay, and it's making its decisions, okay, and currently it's making its decisions and giving the data about patients during 2026. So it's making decisions about 2026 patients. Now, what basically happens is it is making assumptions for it's making assumptions with 2022. That is, it's having 2022 assumptions, and it's giving decisions or taking decisions for 2026 patients, which should never happen. Okay, so that's why it says that a model that is trained once and forgotten quietly becomes wrong and gives us inefficient results. So continuous monitoring is very important. Okay, and continuous validation is more important. Okay, so that is the reason why it states that the loop should never be closed and the model should never be forgotten. The quiet kind of forgetting should not happen. Okay, so this is how the clinical model learns through the patterns, and this is how if we try to uh, you know um, get the analogy out of it. So the next one is your generative AI. Okay, generative AI at the bedside. So generative AI, what did I say? It is about, having your generative AI, like, documentation or giving summaries or drafts in clinical workflow. And here I would like to share a real time, like a case study from Microsoft Copilot, DAX or Copilot demo. Okay, so before that, I'll just explain about what we have here. So why generative AI? Why generative AI is used? Because currently it's changing the current clinical workflow. Okay, it's very fast, and any kind of ambient documentation that we need is being adopted by major health systems. So it is at a pace where nothing else matches. So when compared to your generative AI, so it needs a much fast-paced technology with which all of the documentation handling and all of the work synthesis can happen at a much efficient and faster way, rather than depending or putting everything on the shoulders of the clinician or the doctor. Okay, so we have three use cases, or which are ordered here. So you have the ambient scribing. So ambient scribing, what does it mean? It drafts the visit notes from the live conversation. So I will be showing you the demo, the YouTube video of how currently this it can be done. So from a particular conversation between doctor and patient, the AI gives me everything, like, what is the history of the patient, what the patient said, and what is the prescription that can be given, what can be done to overcome the issue. Everything the AI does. Okay, so the biggest time saver for clinicians or even the doctors or the healthcare providers. So this is ambient scribing. And then you have patient messaging. So patient messaging is getting the empathetic replies for any kind of clinician review. It reduces all the inbox burden, but it again raises questions about the authenticity, like, if anything fraudulent is happening or not. So it's again a topic of discussion. Then we have evidence synthesis. So what do you mean by your evidence synthesis? It summarizes all the literature that is there against a specific question. So the use case, the most resistant to error, and because the clinician has to verify it against the sources, so we have something called evidence synthesis. Okay, so these most important thing here is that these models, the generative AI models, can be fluent, but also they can cause errors. Okay, so the thing that we have to make sure here is whatever fluency the generative AI models are giving here, it's not the evidence. Okay, so fluency is not evidence. So before as a clinician, when I have generative AI with me, the technology working for me and making my job much easier, so I would first check what the generative AI has actually given me, and only then proceed it further. Okay, take it forward. So that is the reason why we have to not blindly follow or blindly say that generative AI can do everything. So the human checking is also important. So the journal citation that I have given here is from the Lancet Digital Health. So this actually publishes all the substantial clinical safety scholarship on all the LLMs, the large language models in healthcare related workflows. So this this is why this is here, because when I talk about generative AI, we are not only like talking about the hype that is there around it, but we are actually into serious kind of peer-reviewed literature that we already have in place. Okay, so the video link given here is from the Microsoft, as I just mentioned, Microsoft Nuance DAX Copilot demo. So it is a most polished, if I can say, vendor neutral feeling demonstration. Okay, for ambient documentation that is publicly actually available. Okay, so let us first look into what it is. I have many examples to show actually, but I don't know if time will permit me. I will try to show you few of them. But then, okay, we'll see. If time permits, we can go through everything. Otherwise, I will just share the slides and we can just look into it later. Okay.
My voice is not audible, ma'am.
Oh, okay. 1 minute.
Yeah.
I think I need to do something here, right? For the
Yes,
audio.
ma'am, yes. But the audio is not.
Uh, okay, can you hear now?
Able to toggle back and forth.
Yes, ma'am. Yes, ma'am. Now it's okay.
And when we go over some of the workflow capabilities of this
Yeah, okay.
technology, you'll see why that's so important. Now, also on the mobile app is you can see a list of summaries. So these are all of the encounters that I've completed today. A scheduling feed is not required to use DAX Copilot, and so we would simply recommend that the clinician use 2 patient identifiers such as name, age, date of birth, or gender to be able to identify the recording. Now, to begin the recording, I can go ahead and press the plus button down in the lower side of the mobile application. This takes me to the screen and just makes me aware as a clinician that I need to be sure that I've gotten appropriate consent from the patient in order to use this technology. Now, for the purposes of today's demonstration, my colleague, Caitlin, is going to be the patient. We're going to go through a mock clinical encounter, and she's going to be playing Maria Gonzalez, who's 35 years old, coming in for a cough. So, hi, Maria, how are you?
I'm doing okay. How are you?
I'm good. Are you ready for me to go ahead and begin the recording?
Yes.
Okay, let's begin. Maria Gonzalez is a 35-year-old female who's here today with complaints of cough. So, Maria, why don't you tell me a little bit about what's going on with your cough?
So about 2 weeks ago, I noticed a little tickle in my throat, and then it's gotten progressively worse into like a deep, rough cough, where I've even been coughing up some like green mucus. Oh, I've just had a little bit of a headache.
Yeah.
Nice and...
Yes. And can you think of anything that might have caused this? Is anyone else sick?
So I went on my friend's bachelorette trip 2 weeks ago, and one of the girls came sick.
Okay, all right. So where did you go?
We went to
For the barbecue and the music. You traveled. Do you have any shortness of breath at all?
No.
No. Okay. And have you noticed any leg swelling or anything?
Nope. I wear my compression socks.
Physical exam.
Okay.
I don't want you to worry. I'm going to be calling out some of these exam findings, but I'm going to let you know what that means when I'm done, okay?
Okay.
All right. I'm going to go ahead and just start by pressing on your face here. Any pain when I press on your face?
Just on my forehead a little bit.
Okay. All right. On facial examination, there's mild pain to palpation of the frontal sinuses bilaterally. Just going to look in your throat. Okay. On throat exam, the uvula is midline. No evidence of any peritonsillar exudate. On neck examination, there's no cervical adenopathy present. I'm just going to go ahead and take a listen to your heart and lungs, okay?
Okay.
On cardiac examination, the heart is in a regular rate and rhythm. I don't appreciate any murmur, rub, or gallop. And on pulmonary examination, there's chorus rhonchi bilaterally and occasional expiratory wheezing. So, Maria, what does all of that mean? That just means that you do have a little bit of wheezing in about my plan, okay?
Okay.
So for your cough, I do believe that you most likely just have a viral symptom. If your chest x-ray comes, it's 1 to 2 puffs.
Okay, I'm just running it
About any of that.
forward.
Oh, I haven't.
Different time.
Yes.
Yeah, okay. All right. Any questions about any of that?
No, it all sounds good.
I was able to generate from that conversation will be.
Okay, now this part
So in
is
a moment,
about the generative AI that I just said. Just observe what the doctor is doing next. So the conversation has been recorded by DAX. And then the next thing is the generative model getting into action.
we'll be able to see what the AI was able to generate from that conversation. We'll be able to see this information directly within the mobile application. Now, the clinician can go ahead and start editing this information directly within the mobile app, should they choose to do so. So we can see that it's already back. Let's go ahead now. Let's say I'm back at my desktop and I want to go ahead and start putting this information into the EHR. I'm going to go ahead and open up my desktop version of the application. And I can see that Maria's summary is right here. Let's just take a moment to go ahead and review what the AI was able to generate from our conversation. So it talks about how she had a tickle in her throat, it's gotten worse, coughing up green mucus, no blood with cough. She has a little bit of a headache. She thinks she's drinking enough fluid. No facial pain. She went to a friend's. Now it says here bottled trip. Now I can easily change that to bachelorette 2 weeks ago. I can easily do that using Dragon Medical One. And it also talks about her pulmonary embolism that she had, and she sees her hematologist. Now, the way that you see this output delivered to the clinician, it will be delivered in standard fashion, in this standard format based on specialty. And so on the physical examination, you don't have to say the physical exam in front of the patient if you don't want to. You can always step outside of the room, press the record button, and just speak your physical exam findings. So that's one option. Alternatively, you can continue to use any macros that you've created within your EHR to augment this output. And then DAX Copilot is able to go ahead and get the diagnosis as well as the medical decision making for each issue talked about during the encounter. So we talked about her cough. We're going to go ahead and give some guaifenesin, albuterol, schedule her for a flu vaccine, and she's going to follow up with her hematologist for her pulmonary embolism. So I think that that's a very succinct and complete note. It really didn't need a lot of editing except for the bachelorette party, if I have abilities of getting this information into the EHR. So you can see on here my Dragon Medical One toolbar. This is newly redesigned, takes up less footprint on my screen. I'm going to go to Maria here. And now there are a couple different ways that a clinician can get this information into the EHR. Again, this technology is not one size fits all. Each clinician might use this technology a little bit differently, and that's why it's going to be so scalable throughout healthcare organizations. So the first way that you can go ahead and move this information in is by simply using your voice to move all of the information into a blank template. So I can very easily just go to my PowerMic Mobile, transfer all. So you can see how easy that was for me to move all of that information over with just my, I've already seen it within the Dragon Medical One window. Clinicians use a lot of templates and macros within their EHR.
Okay, so that was the glimpse of what I wanted to share with all of you about the generative AI, being in action, where the LLMs and also the multimodal models are, moving at a much faster rate, handling all the clinical workflow documentation and the synthesis work. So this will actually help the clinicians at a much easier and a faster rate. So next we will look into the next slide, which is okay. So the next one is, it shows the pairs of bar chart, which actually says something about with the support of a model and without the support of machine intelligence, how does, the medical workflow or the medical applications actually work. So 70% less time, the less time on routine image triage. Why do we say that? Is because when we have a machine learning model or the AI model support, we say that, the consistency and the speed can show up in your clinical AI, like the value actually shows. So the speed with which we can look into the problem and detect that there is an issue, and we can say that, it doesn't outperform the experts, the health providers, but the speed and consistency is there, right? That will actually increase the pace and the scope that is there for us to provide a better solution for the patient. Okay, so the model, we can say that, when I say that I have the support of the model, I don't say that the model is super smart or it's more smarter than the radiologist or than the clinician. I only say here that it's more faster and more uniform and it gives more consistency. Okay, and by doing this, what does it basically do? What it basically does is it frees up the clinicians and it takes off the burden from them, or the judgment that is given from the clinician when the problem is actually, spreading to be a crisis. Okay, so initially, at the initial stage itself, the AI takes up the, work of identifying and then detecting. So that's why we say that it's a triage time. And then we have the aspect of missed flags, that is the detection. So when human intervention or from the healthcare provider, might be the flags have been missed, or might be the patient himself or herself have missed the flags, the red flags that are there. So when we have the support of the model, these flags, missed flags, without the model, when we compare with model, it's much lesser, the number of missed flags. And then the report delay, the delay that we get from the reporting, like the radiologist writing the report for the scan that we did just now. So for human beings it might take a lot of time, but just now we saw an example where AI gave the report, gave the assessment plan, and it was sent to the patient through the app itself within fraction of seconds. Like you don't need much of a time. So that is the reason why we say that 70% less time on routine image triage through this illustrative bar graph that you can see. So time saved is is a more underrated thing, if I would say. Why? Because even if few minutes or few seconds of thing is there, like the missed flags are on records. And even if we say that the detection of triages or even the reports being generated is much faster, just because human life is involved, less time saved is, I would say, a word that gets more underrated. Okay. And the the time that is actually shown here, and also the accuracy proxy, that is the missed flags, and the downstream effect for the report delay, all of these demonstrates that the value is multidimensional. Okay, so each category, if you take, is turning it. Of course, we know that it's interesting, but when we describe it together, and when we put it together, we can say that the actual clinical workflow can improve drastically. Okay. And the literature evidence that we have, I have put over here. So it has already got published in IEEE Transactions on Medical Imaging. It is a long-standing a technical home for deep learning research, especially in radiology and pathology. So why I've put the citation here is that, so medical AI has been there, grounded from if I would say, from a decade ago. So it's grounded in decades of literature. So it's not a sudden invention. So that's the point to be highlighted over here. Okay. The next one, when we look into the broader horizon of your machine intelligence, and when we say that we have quantum computing in place, we know that it is a classical explanation where we say that it is a bit versus a qubit distinction. Okay, so when it gets connected to medical field, we have the possible fields of protein folding, or even drug binding example, where quantum computing can give us more advantage over normal traditional processing system. So here you can see that it gives me, when I have bits, it is having two great circles where you can see a label 0 and 1 for a bit. Okay, so a single atom decorated circle is described as a blend of zeros and ones for a qubit. So a blend of 0 and 1, which means that we have many possibilities held together. Okay, so that is the reason why we say that it is a blend of zeros and ones for a particular qubit. So it the most hardest, the issue in like in biological applications, the most hardest problem is how a molecule folds or how a drug gets binded. Okay, so these are the most exploring vast combinations that can be exactly addressed using your quantum computing. So this is where your quantum approaches may actually come to rescue, and they actually make us go and deep dive into how we can explore the enormous number of possibilities that can be achieved for how a molecule folds and how a drug binding process happens. Okay. Okay. Where does quantum computing converge or come into a picture for your healthcare? So in the previous slide, I told that, the most major problem in biology is to know how a molecule folds or how a drug gets binded. So these days, quantum machines are, much smaller, fragile, and noisy. So mostly when we say that we have quantum in medicine, results are, simulations of small molecules, like which are promising but not productionized. So we can say that, classic computing reads the library one book at a time, but quantum computing glimpses many pages at once. Okay, we can say that it sounds imperfect, but it captures the very nuances or the essential conceptual shift that we need for especially when we want to deal with healthcare related applications. So the first thing is about your drug discovery. All the big pharma is actively investigating, investing in this field. Like it is closest to the real impact. And then you have protein folding, like we just discussed. So it is a kind of more interesting research, but all the classical methods that we have currently outperform quantum computing for most cases, but still the research is still happening in this field. So we still need more innovative solutions for that. And then we have smarter models. This is still speculative, but there's no clear advantage where we can say that quantum computing is outperforming. So quantum assisted learning is turning out to be too complex for the machines today. So still, this also is a more fascinating research field. And then we have security for the data. So quantum resistant encryption is actually turning out to be more real and attention seeking aspect, but it's defensive to be more precise, not transformative. So we say that securing data is actually the most important attention seeking thing to do. Okay, so most of these are at research stage. So we are not yet, we are still exploring the concept of all of these vast combinations of how we can be working with a quantum computer in the field of healthcare. So this is an interesting topic where if you are interested to combine quantum computing with healthcare, so you can explore all of these aspects. Okay, all right. Then we have an interesting case study here where we have screening eyes that would go unseen. So what do we have here is we have a problem. okay, where we say that diabetes or the problem of high sugar levels in a body can actually damage the retina of your eye. So early detection of this problem can actually save us from getting blind. But specialists are actually we don't have much resources. So we say that diabetic retinopathy AI is the word here, the phrase here. So it is a most studied, most deployed, and most publicly validated clinical AI application that we have in place today. So the problem of the diabetes and the retina's health being connected here is addressed, and AI comes to the rescue again. So the model actually doesn't diagnose, but it warns us, it triages, it gives us a specific warning, okay? And patients flagged by the model can still see a specialist, and patients not flagged are still rescreened on a periodical basis. So this is the deployment of the pattern for almost all the clinical AI, and the this case study that you can see lets you to say, or allows you to think that AI comes to the rescue and lets you to state it more concretely. So it reaches to a point where humans could not reach. So first, like filter it if it is a problem or not, and then go about with the preventive solutions. Okay, so the approach is it gets into account all the photos of your retina, and then it creates, or it gives the warning, or it flags the warning. Okay, so it takes minutes for that to actually happen, not weeks. So results is got during the same visit. And even in rural areas, this can reach. So no on-site specialist is needed. So you can see that, AI is, when AI is used in healthcare, so the society is getting advantage out of it, okay, a lot of advantage out of it. And specialist focus is human review is also, as a final check. And this is actually you can find it in the literature, okay, where I have given the the reference. So it's called the JAMA reference by Gulshan et al, published during 2016, and it is if you can say, it is one of the most cited papers in medical AI. Okay, so you can go through this paper if you get an access to it, and see how diabetic retinopathy screening is done and how it has helped in the field of healthcare. Okay, so again, I have a video here. Later I will share the slides with the team here, so that you all can go through and see how AI actually detects diabetic eye disease. So I think I still need to cover more slides, and okay, I'll just play this video. I'll just quickly take it forward, because I have a lot of things to cover yet.
Hi, everyone. So I'm Lily. I work on our medical imaging team in Brain. And in a previous life, I was a doctor, and I've been repurposed as a product manager at Google. So one of the projects that we've been working on in our group is using deep learning for retinal imaging. In particular, we are looking at a disease called diabetic retinopathy. So that's, other than a mouthful, it's actually also the fastest growing cause of blindness in the world. There are 415 million people in regular screening. So every guideline sort of worldwide recommends about once a year screening. And it's because this is pretty asymptomatic until you reversible vision loss. And then it's a little too late to intervene. Sister, and then a doctor grades these images. Look for these little hemorrhages and on the image. Grade 5 from no disease to the end stage R. Doctors to do this task. So in India, there's a shortage of 127,000 eye doctors. And because of this and other sort of systematic issues, about half of people actually suffer vision loss before they're even diagnosed. And so for something that's completely preventable, this is sort of unacceptable. And here is a picture of some of people who are waiting in line to get screened. So even if you get to a place where there is screening, there's a long wait, there's long turnaround time. And so a lot of people end up being lost to care. The other issue is that even when available, that fundus image, and as you can see, when there's no disease, there's in between, there's actually, right? So depending on who you saw, your management would be kind of different. So you know, a little bit more about that later. So where we thought we could help was, let's train a model. And so we actually built a labeling tool. We started off with 130,000 images, and we've gotten much more since then. And we hired an army of ophthalmologists to help us label. And from our 54 ophthalmologists, we got 880,000 diagnoses for these images. And you can see from the previous slide why we did that, because sometimes it took up to 7 reads to get something consistent. Then what we did after we got this data cleaned up and labeled, we kind of used our trusty dusty inception network that works for a lot of image recognition tasks, from cats to puppies to melanoma and now to DR. And we trained it to detect sort of these 5 class predictions, but we also asked it to predict, you know, sort of housekeeping things that may be important for a clinician to know, whether or not this image is of sufficient quality for grading, whether or not this is a left or right eye. Sometimes we get confused. And also the field of view, which is like what part of the retina you're actually seeing. And then we built a front end to this. I'm gonna try a demo here. This is literally what I call a toaster. We try to drag and drop something. I don't know actually how do I move the cursor to, oh, there we are. Okay, so I'm gonna open up a web browser and hopefully that works. But somewhere between moderate and severe, and this is the American Medical Association. And the 2 black dots, if you can actually see it, is
this is how
in black.
You can
That's our
see that the study was done. So I'm just like, you know, not able to play the whole video. So later the slides will be shared, and might be you can go through the entire video and see how look into the illustration and walk through of the entire, you know, DR, the diabetic retinopathy. Okay, so next thing, we are looking into your Internet of Things. So beyond the clinical walls, how can the care be given through the wearables, the implants, and also the connected devices? Okay, so we are looking and exploring into how IoT can come to rescue. So a single person can now, you know, if he or she is wearing an IoT device, so a single person can generate, you know, large streams of data from many different devices at once, be it in shape of a wearable or be it in form of home sensors that are embedded together. So this, you know, the picture that you can see everything connected together. So you can say that, be it wearables or home sensors or even the implants like the pacemakers or the continuous glucose monitors. So all of this together, right, they can converge together, and they can actually give you the overall state or the overall health status of a patient. Okay, so it is like, the line goes like one watch, one monitor, and one app. So everything cannot work in isolation, so we need to put it together. So we need to put it together where variables can, like, the wearables can have, give the consumer or the data information through, like, the heart rate, the sleep, the activity. The implants can give you the clinical data, like what is the current glucose level, and what is the, how well is the heart health. And then the home sensors can, if there's any fault detection, if there's any motion detected, or what kind of environment is there across, if the pollution is more, air pollution is more, or if the state of the humidifier is proper or not. All the post discharge kind of status status reveal. So all that can be got through home sensors. And bedside monitors is continuous vitals being checked, like, when you are in hospital, like admitted as a patient. So together they, if you can see that they cover every IoT touch point a patient can, actually encounter across a care, a care aspect or a care episode that the patient will go through. So um, each when you say that, when I take each stream, if I can take it like separately, it turns out to be interesting. But more, we can say that if currently the clinicians today see them in separate apps with separate dashboards. Okay, so the machine intelligence here comes into a picture when I want to say that all of this together, okay, like, without any issues or without any data latency or anything, it works, of course, independently, more efficiently, but everything should be, put together. So if you were to design a dashboard, if I say that, as a developer, if you want to design a dashboard for a patient who is connected, okay, through IoT technology, what would you actually put? What would you actually use? What would you put on the dashboard? So that is the question that I would like to ask here. So it is a point to be thought about. Okay, so when we have connected patient, okay, with regards to IoT, we have two things here: either edge processing or cloud processing. Okay, two things here. So edge processing is we get instant response, no network round trip latency. So any matters with regards to safety critical decisions is with instant response. And it also works when the connectivity drops. So especially with regards to implants and rural the devices that we implement or we deploy in rural areas. And then a privacy concern is when we say that sensitive data should stay local. So privacy win also matters here. And then limited by device power means small models only can work here. Okay, when the processing power is limited, no large neural networks can be, okay, on a wristband can be actually working more efficiently here. So when I want to expand, okay, when I want to expand, I go into the process of cloud processing. So cloud processing is actually having, vast computing. So vast computing is heavy models, image processing, multimodal fusion, all of that comes here. And then you have combined data across patients, meaning to say that you have all the population insights, which is of course impossible when it comes to edge processing. Okay, and then easy to update centrally means that we have model improvisations done at the that can be deployed more easily, and the update can be viewed by everyone who are using it. So at once the update works for everyone, so that is easy to update. And then needs connection and trust means both technical, that is network related, and ethical, which is data leaving the device. So both of this has to be there. So hence we say that it needs connection and trust. So modern medical IoT systems, right? So they use edge for safety critical decisions, like I just said, okay, for implants related applications. And they use cloud processing for learning and getting the population insights, or getting the trends out of the data that has been collected. So the pacemaker decides locally, the population health model lives in the cloud. So that is the difference between edge processing and cloud processing. So both are, if you can see, edge is if I would say, edge is reflex, and cloud on the other hand is the doctor. So both are of course necessary, and neither can be sufficient. So both are necessary. All right. Then we have heartbeat to an alert. So why do I say that I have a heartbeat and it has to be alerted on time? Because you can see when all the medical devices are connected, the pipeline should follow. So such a pipeline, such a such a workflow will make invisible process also visible. So they can actually the devices can actually first sense a vital sign or a vital indication, which is limited by sensor accuracy and skin contact. And then the signal travels to the phone gateway where the transmission is happening, or even for that matter, the hospital server. And then we go about with the interpretation, that is the model checks for any warning patterns limited by training data or even the false positive rates, and then goes in the alert, like a clear message reaches the right person. Again, this can be limited by the design that we do for the alert system, or even with the recipient attention. So the care team has to be notified on time, and each each handoff is a failure point, is also a point of failure. So we have to make sure that such a failure should not be there. So a perfect sensor, if I can say, with bad transmission is useless. So a perfect model with bad alerts is again dangerous. So I can say what we need to make sure here is the pipeline only works. This can only be successful when every step works, when every step turns out to be successful. Okay, so that is the thing about your Internet of Things. Okay, the next is again a case study related to IoT. I'm not going to go into the video. So again, here I have cited the literature from Apple. Okay, so this it says that the Apple heart study by Perez et al. During 2019 in the literature. So it enrolled nearly 400,000 participants. So you can find this in the literature. So what did they actually do is they looked into the heart health of the so many participants, so many patients, and they got about the information with regards to their atrial fibrillation. So atrial fibrillation is about the heart health. So it is about an optical PPG. Okay, an optical PPG, so optical lethysmography, if I'm not sure if I've taken the pronunciation correct. So what it basically does is it measures the pulse rhythm through the skin using the LED light. So irregular pulse intervals suggest and it gives the result to the fib app or the watch that the person is wearing, which was from Apple, and then it prompts the wearer to take a single lead ECG for confirming, for final confirmation. So why this was done was because to check through the smartwatch, to study the the heart health of the people, and through an Apple's through the device or the smartwatch from Apple. And here you have the literature, and you can also see how the watch works through this video. So later you can go through it. And why we have this is because whatever silent things are creeping in, and we don't have a glimpse of it, or even our healthcare provider might miss it, the wearables will actually come to the rescue. So millions were screened, and early detection were flagged, and also the false positive and the trade-offs were addressed. This says, or this puts forward the fact that though we have trade-offs, and though we have disadvantages, it can save many patients by early detection. So patients were convinced with a watch diagnosis, and then the clinician's job here is to again re-examine, confirm, or refute any kind of the results that were confirmed by the watch, and then take the further decisions. So the Apple's own demo is very clean and accurate and consumer friendly. If you can look into it later. So it lets you to discuss what a patient can understand and what misunderstandings can happen, and how you can use the device for your for getting the early warnings. Okay, so this was the case study. Okay, the next one is about the 4 parts that we must be aware of, the 4 challenges, which is the security, interoperability, reliability, and alert fatigue. So why we have this is because whenever IoT is involved, we should make sure that we should all of these aspects we should be aware of. So security, what does it mean? Every connected device is under attack. Okay, so implanted devices have to be have to be demonstrated for any kind of vulnerabilities, and hospital networks have also they should be immune to any kind of insecure or security attacks. So it's optional, security is optional, but sorry, security is if you can say that security is not optional, so it is the prime concern for patient safety. And then you have interoperability. Interoperability is where devices of course can't speak with each other, so the entire load of stitching together all the devices and putting it into in one place together, getting an overall picture from the devices itself is a safety. We should make sure that we are not getting into any kind of issues. So interoperability is more important. So the cognitive load of stitching all the devices together, so that is getting a kind of coherency, getting a kind of consistency when many devices are involved, that is more important. Reliability is where batteries can die, signals can drop, networks can go into issues or breakdowns, so devices can break So we have to make sure that there is a survival plan, or a plan B, where even during offline situations the system should work, or even if they eventually fail, a patient should not be left to left to face the problems or the failures, and just because of that failure the patient's health should not get compromised. Okay. And then you have your alert fatigue. So this is a most underrated. Again, clinicians who receive many low quality alerts gradually stop noticing the high quality ones. So it's more important that real time alerts arrive, and we give priority, so that it doesn't get dismissed reflexively. So the phenomenon should be well documented, and also we should make sure that patients get attention at the right time. Okay. All right. The next one is data analytics. So big data, we know that you have the 4 V's involved, where volume means you have humongous data, velocity means the data should travel very fast, variety means we have many different types of data like images, video, like different kinds of data, so variety of data. And veracity means any kind of inconsistency or messy or missing data. So all that also should be handled with care. So these are the as you can see, are the important aspects when big data is involved. Okay. So um, when we have this big data in place, 4 questions has to be answered. So the first one is descriptive. What happened? Okay. What happened? All the dashboards, the reports, the summaries of the past event, that is descriptive. Okay. And then diagnostic is why did it happen? Okay. Finding the reason behind a particular outcome. Predictive is what will happen in future, forecasting any kind of risk for an individual or an entire population. And then prescriptive means what should we do in future. Okay. Recommending what is the best action. Okay. Best action ahead. So most healthcare systems today have the first 3, which is your descriptive, your diagnostic, and your predictive. Okay. So if you take the AI thing into picture. Okay. So that is with the big data analytics. Okay. So when you look into the case study, we don't have one particular patient here. Okay. When big data analytics is involved, we see an entire population. Like, if I say that we are into like something like COVID pandemic that happened. So during that case, we have thousands of records or even millions of records, where we want to see how how the diagnosis can happen, how the solutions we can give about, and how we can go about with all the thing that has to be given in the first place. So when I put that concept into a case study, we have a case study which has predicting sepsis before it strikes. Okay. So sepsis, I hope you all are aware that it kills quickly, and early detection is very important. Okay. And we have many like many studies in the literature, so I've cited here. And we also have the video which gives us an understanding about how machine learning can predict the sepsis. Okay. So the approach is the analytics engine continuously fuses the vitals, the labs, and the notes to score each the patient that is at risk of getting the sepsis and getting killed. So a predictive model runs continuously against the EHR. Okay. And whenever a risk is noted, or identified, the alert is reached, or the alert reaches, or the right team is notified. So once it's there, the action is taken from the clinician. So detection is got before the collapse happens, and many feeds are got just to be sure and avoid all the false alerts. Okay, and it also is embedded into the workflow. So we have this as a real case study with regards to big data analytics. So when I put that across like a different possibility here, from average patient to one particular patient. So you have a 4-layer model of precision medicine here. So first you have the genomics, then you have the phenotype, then you have the environment where it actually has to be applied, and then you have the history, which is recorded over time. So genomics is your DNA. Okay, what your DNA disposes, and the most studied layer. Phenotype is how your body actually behaves, where genes meet the environment, okay, in the observable format. And environment is your diet, your pollution, your stress, that you're going through, the community you live in, the geographical area that you live in. Okay, often this is the most largest casual contributor, often the least well measured aspect. And then you have your history, where your record gets recorded, where your details or your data gets recorded, like what happened, what worked, what did not work, and all of that. Okay, so each layer alone is incomplete. So genomics alone is like without context is destiny. So so we can say that only when we combine all of this, we will be able to say what works for most of the people, and what is most likely to work for the person who has come for the diagnosis. Okay, so that is, again, you can find that from the literature. Okay, and no analytics without trust. Yes, of course, I've already said this. So patient privacy is important. The quality of data that is being collected is more important, and bias should not be there. So the model should check if it works fairly over all the population groups. And of course, patient consent is more important. Without consent, we are not supposed to move forward. Okay, and then we need to go to a point where all of this can merge together, right? So we have seen all of this separately. So now we can see that we need to merge it. So the real revolution isn't about a single technology. So if I say that I want to combine all of these three, that's why we say that 1 + 1 + 1 is greater than 3. So all the like individual advantages of all of these technologies, when we embed together, becomes greater than 3. So it is a loop that they form together. Again, it goes back to the first slide where we started. Okay. Can you see my screen now?
Yes, ma'am. Yes, ma'am. Visible.
Okay.
You can. Ma'am.
Okay. Just 5 minutes. I'll be finishing it. Okay.
Yeah. Okay.
So
Fine. Ma'am.
okay, after the point where we have seen that all of these technologies converge, we have to have these 6 tensions in mind. 6 tensions, as in all of these aspects, we have to make sure we kind of address it. So bias and fairness is when we train a model, and the few the harm that can happen on very few, okay, rather than many. So this is one of the most important. So the bias and the fairness should be considered. Privacy versus utility, more data, um, more data, like if it's there, it's more good. So again, it gives us the tension that it's the thing is very real and it's not solvable, meaning to say that it raises the stake if it leaks. So privacy is more important, okay. And we have to make sure the systems are not vulnerable to any kind of privacy attacks. Explainability is where a clinician can justify a decision when they can't fully inspect or fully see the condition of a patient. Some models work better when than they explain. So others explain better than they actually work. So that is explainability. So we have explainable AI in place for that. Accountability is when an algorithm gives an error, who answers for it. Often it's genuinely unclear, but the answers that you get, shapes all the deployment and decisions that happen within the medical workflow. And then you have your access and equity. So will all of these tools actually widen or close the gap? Mostly the answer is yes, it's widening, unless we work to close the gap. Okay, so we have to make sure that research helps us to do it. And then human in the loop, yes, automation should support the clinical judgment and not, erase it. So it's more important that it should help besides and stay besides the clinician or the doctor. The question is, how much support is too much? So that is more important here. Okay, so that is human in the loop. And then you have how your bias enters and how to catch it. As we know, whenever we are training a data, skewed data should not be there. So training data overrepresents some groups and underrepresents other group of data. So often it reflects any kind of historical inequalities that we have in who has got studied from the population and who has been left out. So we have to know how to learn that skew and how to inherit or how to improvise that particular imbalance and get things in place. And in deployment, patients that are in under represented groups are actually misserved. So often they go invisible. So because the outcomes data is also uneven when we look into it in a more collective way. So we have to make sure that this bias should not be there. So that is the next ethical concern that we have to, as we look into the healthcare applications, we have to make sure that all of this has to be addressed. Okay. Now, what is a simple framework for responsible use of the clinical data? One is, beneficence. So, which means that does it genuinely improve the patient outcome? The next is non-maleficence, which means that have we tested where it could cause harm and where actually including the unhappy parts, the subgroups, the false positive, all of that comes in over here. And then we have your justice. Does it serve all the patients fairly, not just on average, but across every group? Okay, that is more important. And then autonomy is, do the patients really understand and consent to how the tool is being used, or is the model being used invisibly to them? So all of this is a simple framework for the ethical or responsible use of the clinical data. So when we look into again the ethical concerns, trust is built and not assumed. So we have to make sure that the trust is actually built. So trust is only built through, if I can say, only through evidence and accountability, not through hype or polished demos or false narratives. So patients and clinicians adopt what they trust. The rest, has to be, quietly shelved. So it's more important that trust comes from transparency, evidence, and clear lines of accountability. That is, if anything goes wrong, who should take the responsibility? So be clear about what the tool does and what it doesn't do. That is transparency. Okay. Validation on real patients is your evidence, and who's responsible when things go wrong is accountability. So if the answer is algorithm, the deployment should not be ready. Okay. And accountability is more important when patient's health is involved. Inclusion is involving the patients and the clinicians in the design from the scratch, and tools that are designed without the users inception or without the users feedback get used only under duress, or it quietly gets forgotten. So you have to make sure that all of this is there in place. Okay. So what is the future road ahead? What do we have now? We have ambient documentation that we saw, that the YouTube video that I showed to you. We have wearable screening, that is wearables through which we get screened, remote monitoring we have, and imaging decision support we have. So this is proven clinically, and it's spreading across the world. What is emerging through research, that is, it's real but it's still in maturity stage, is multimodal patient models, personalized treatment, predictive population health, and federated learning in healthcare applications. Now, what is the future ahead? The ones who want to do research in, combining technology, IT, IoT, and everything together, along with medical healthcare, like healthcare, intelligent healthcare, quantum drug discovery, very, very interesting topic, autonomous care pathways, whole body digital twins. So this whole body digital twins, one of the groups in my university is currently, doing the research in this. And then you have AI designed therapies. So you have to keep your eyes open with optimism and see how all of this can lead to innovative solutions, and you have to make sure that the equity gap, the innovation that reaches only when the injustice is there, that gap should be filled. So the most consequential risks happen by default. So unless you deliberately bring into picture. And then skills, when we lean on the tools, over reliance should not be there. So the radiologist who can no longer read the scans without AI assistance is something which states that it is a failure of the education that the radiologist has actually got, not the failure of technology. Okay, so the proper embedding between the human and the AI should be there. And then the surveillance creep is, when we get continuous data, the monitoring should be there. So the same monitoring that can serve the care or quietly serve the control, you have to make sure that which one you're addressing. The same monitoring that can prevent a readmission can become unwelcomed observation. Okay, so you have to draw a line between governance, like what can you govern or what can you monitor, and that the line has to be drawn by humans, not by technology. So that is the surveillance creep over here. And then you have the hype cycles, over promising solutions, or the trust that can actually disappear or be forgotten, trust that real progress depends on. All of that should not be given on a much hyped rate. So every disappointed clinician makes the next legitimate tool much harder to use, okay, much harder to deploy. So over-promising erodes should not be there. Okay, so let's build the solutions for intelligent healthcare more, smartly, and let's make sure that, technology is used in a more sensitive way. So people should actually trust the idea that, technology is there for us to help, for us to, make our lives easier and not the other way around. Okay, so I'm done with my presentation. I hope you all have gained some knowledge out of my discussion. Any questions, you're welcome to ask. And I will be sharing the slides so that all of you can go through the papers and also the video, the reference videos. Thank you.
Any queries from some? Yeah, thank you, ma'am.
Thank you. Yeah.
Any queries from the audience? You can post in the chat box. Any queries, please, you can post in the chat box.
Thank you, Dr. Geeta. Thank you, ma'am. My pleasure.
Yeah. Thank you, ma'am. Good afternoon to one and all present here. Myself, Professor Anand, Additional HOD, Department of CSC, Dr. MJ Education Research Institute. It is my proud privilege to propose the vote of thanks for this intellectually enriching session conducted as a part of 6 days virtual faculty development program on transformative approaches in computing paradigm, machine intelligence, and quantum computing. On behalf of Faculty of Engineering and Technology, Department of Computer Science, Center of Excellence in Computational Intelligence and Medical Technology, and the Department of Cybersecurity, I extend our heartfelt gratitude to our esteemed resource person, Dr. Shaik Shabana Anjum, Senior Lecturer, Tailis University, Malaysia, for delivering an exceptional lecture on intelligent healthcare, harnessing machine intelligence, IoT, and big data analysis for the future of mission innovations. Your scholarly insights, interdisciplinary perspective, and missionary approaches towards intelligent healthcare technologies have profoundly enriched our understanding of emerging technologies. The depth of your expertise and the clarity with which complex concepts were present truly inspired all participants. Thank you, ma'am.
Thank you, everyone. For any research collaboration, I'm always open. Thank
Sure,
you.
ma'am.
Thank you. Thank you.
Queries from audience?
Bye-bye. See you.
Yeah.
Have a great weekend.
Yeah, thank you, ma'am. Thank you. Thank you.